So now we do explicit computation group cohomology. In this section, we will find a nice resolution which will let us give an explicit description of cohomology groups. To do this, we need to give another interpretation of the derived functor. We give another interpretation of the derived functor. We first suppose that G is discrete. Okay, this is the most simple case, the easiest case. Discrete. You don't have to worry about continuous or not. This will also give motivation why strange formulas arise. We first remark that for any G mod M, we have the fixing point of M, a fixing point by G on M is homomorphism in the category of G modi from Z to M. So to write more explicitly, as we showed in the last section, when G is discrete, this is the same. The G modi, the category Z modi, is the same as category group algebra ZG modi. This works when you put on the trivial action G of ZG, the trivial action. Well, maybe you ask, why don't we just put ZG here? Well, maybe it works. It looks like this still works if you put this with trivial action, if you can. The point is that element of here is just determined by F1. Since it's the G modi, once you know the image of F1, you know the image of any Fn. And to say why this is a fixing point of G, we just check what are those elements of M that are possible candidates of F1. So if you first apply F to 1, then you apply in G. Since you are G modi, G linear homomorphism, you should have this. But as we said, G acts trivially on Z. So this is F1. So you see F1 must lies in the fixing point of G. And this is the only requirement of F1. So okay, this is it. In fact, this is a factorial equality. Therefore, the functor of fixed points is equal to the functor, its home functor. Therefore, we have that for any G modi M, the nth cohomology group is the same as the nth exterior group associated to the home functor of ZG linear morphism starting from G. So here's G. Here we put our M modi here. But we saw about that the right hand side can be computed using projective resolution Z. So this position you can compute with projective resolution. This position you compute with injective resolution. So we can compute with projective resolution of Z. This is what we are going to do. Denote PR the freezing model with basis the R+1 tuple, and endowed with G action given by component wise multiplication. Let's say this lemma. For any R big equals 0, the G modi are constructed as about is a free ZG modi with basis. So this PR is R+1 tuple. It's R+1 tuple with each position taking element from G. The G module PR constructed as above is a free ZG module with basis the R+1 tuple times this. When we define PR, we saw it is this lemma says for any R bigger or equal than 0, the G module PR constructed as above. Notice it is a free Z module with basis all the R+1 tuples. So PR is zeta G0 GR with any Gi in G. So they are so very big. If G is big, then it's very big. Direct sum. Now you want to realize it as free ZG module. You claim you want the basis of this type. Here the author claims we have to just prove the morphism from PR to a G module M, so as a G linear morphism is uniquely determined by the image of those elements. Well, more directly, by definition, what we have to prove is that first, as a ZG module, those elements generate this PR as ZG module. Secondly, they are all linearly independent. So the first thing we see, they are generate. These two things together says it's a basis. So any element of PR is the form N1 times G01 GR1 plus M times G0M GRM. But it is N1 times G01 1 G01 inverse G02 so on G01 inverse GR1 plus NM times G0M times 1 G0M inverse G1M. Sorry, so here is G11 GR1 so on, finally is G0M inverse GRM, because as a ZG module, the action of element of ZG acting on this ZG module is by first apply G acting on it by the way we defined like this, component wise, and then you apply the element of integer on it. In the way you defined to be the free Z module. Just formally if you want. The second thing is you have to prove it is linearly independent. Okay. So if again we simply write the element of Zg. So element of Zg, the general form should be, as we saw, should be like this form, summation of element of Z times elements of G finite sum. So you see, if you have a linear relation, let's denote this by alpha m, this is okay. So alpha times 1 G1 GR I denote all this like with 0, okay. Zero, 1, 0 R T 1 G0 G T1 to GTR. If this equals 0, then what we got, we just look at the first position. Firstly, let's first deal with the easy case. We do not take a general term, it's a little mess. We just do the element of the form. Here's N0 G0. Here is NT JT. So the summation gives you N0 G0 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 1 G0 G0 R plus N1 GT JT JT1 GT JTR You see, since those elements are all different, then those elements must be different. If any two of them are the same, it means G0 equals GT, for example. Then since the remaining elements are all different, the multiplication by two same elements must give different elements, so they're different. And if they're different, then just as a Z module, they are bases, so C0 implies an I are all 0. Okay. And in the group algebra, a general term like this, and if the coefficient of Z and I is 0, it means this term is 0. Actually, we define to be the sum with finitely many non-zero coefficient in Z. It's a general term of the group ring. So this is the easy case. For the general case, you do it similarly, okay? Now we define differential from this PR to PR minus 1. This is our candidate to be a projective resolution. It's a free ZG module, so in the category of ZG module, it is a candidate of the projective modules in the ZG module. If I define a reasonable differential, it gives you a resolution. By defining this Euro wave summation of ending a plus or minus sign depending on the position of the element that is ignored. Okay. Remark, it is a morphism of G module and the composite of the differential next to each other are 0. In fact, one can check it. Okay, I do not check it here. So we have a complex in our case we put P0 to be ZG and we define morphism epsilon by mapping G to 1. Then our lemma says that this complex is exact. This is a projective resolution. Actually, by our definition, PR is R plus 1 typo, with the element starting from 1 and any other position, arbitrary element of G as basis of this free ZG module. So P0 is just a free ZG module generated by one element. Okay, so it's just isomorphic to ZG as a module. This complex exact tells us we have a nice resolution. Remark, since Z is free as a Abelian group, the cohomology of home Z p dot m, which is exterior group, the i's exterior group Z from Z to M, and Z linear. Actually here it states something very strange, but okay. Notice here what they want to say is the exterior as Z module is trivial, but this is obviously trivial. If we compute this as Z module, you can choose an injective resolution or M, we call it G or I, but your functor home ZZ here, this is projective, so this is the exact functor, so the cohomology group must be trivial. Why do he mention this? He's just saying that okay, our PR is a free ZG module, but if we only consider it as a Z module, then the cohomology of this is trivial because it's symmetric. It means the exterior, whether you compute this with a projective resolution Z, like here in our case we use a projective resolution Z, PR is the same as you use the injective resolution with M, which tells you directly this will be 0, so we know the cohomology of this must vanish. and the complex, since it is exact functor, this is exact functor, this tells you vanish, and if this is vanish, this tells you this must be exact, because the cohomology group are all vanish means after applying this factor to a projective resolution it's still exact. But one can also prove this fact using the homotopic given in the proof. This will be useful in the context of continuous coaching. Continuous coaching is when we are in the case where G is not discrete. In this case, we are not likely to say that the category of G module is categorically equivalent to the category of ZG module, which is really a category of module, so has enough injective and projective. When G is not discrete, we do not have enough projective. And the argument like this, choosing PR to as a projective resolution of Z, and then to compute group cohomology with G doesn't work. It doesn't work is simply because this works depends on the fact that we can translate G module into ZG module, and we actually construct PR as a projective resolution of Z as ZG module. But when G is not discrete, it's not the ZG module anymore. Since PR is free as a Z module over G R+1, for any G module M, an element of home as a Z linear from PR to M is uniquely determined by the image of a basis. So we can identify as Z module homomorphism from PR to M with as a set from GR+1 to M. By our definition, PR as a set, it is just all the R+1 dipoles taken from this product group. Okay, if you just consider it as a Z module, then of course it is a free Z module generated by all the elements. I'm sorry, the PR is not as a set all the elements of the tuple. PR is the free Z module with basis all the elements of this product group. So if you just consider it as a Z module, so it's a free Z module with basis. Here of course it's determined by its image of basis. So the homomorphism as Z module from PR to any Z module M is just as a set from this basis, because GR+1, the whole product group is its elements are basis. So obvious, but moreover, if you want to consider more than homomorphism as Z linear but G linear, then you have to require something more. Actually, here when we write G, we're still in the case G is a discrete topological group. When we write G, actually we mean in the category of G module, which is the same as the ZG module. So it's the same if you write it here on ZG. So you not only have to regard it as a Z linear, but also as G linear. So based on what you have here, you have all the candidates to become a Z linear homomorphism. It's the homomorphism as a set from GR+1 to M. But within all these candidates, you have to restrict on one more restriction, that is, you have to require it's fixed by element of G. So phi acting on element acting on G must equal G acting on the image of phi. So the homomorphism in the category of G module from PR to M can be identified with the set denoted by CR twiddle GM of functions which satisfy this condition. Such functions are called homomorphism R cochains of G with values in M. Okay, with values in M. Now if we consider the complex homomorphism from P, R to M, the category of G module, and we compute its cohomology, we obtain exterior nth exterior group equals cohomology group, nth cohomology group of G. We write down explicitly the co-boundary map of the complex. It's like this. So as you see, this twiddle RGM, actually it is home G P R M. Yes. So by using the projective resolution of the category of G module to compute this group homology, but it's the same to compute the complex of homogeneous R cochain. So you have to write explicitly the differential, which is writing exactly here. Of course, this differential is just got by translating the differential we defined on PR to PR minus 1. We just translate it by this relation. In fact, we have an isomorphism of groups where the CR without theta is a group of set function from GR to M. The isomorphism is given by, so R by the isomorphism, we have any element fixing G. How do I send it to a set function from GR to M? CR twiddle is the function and G linear maps from GR minus 1 R plus 1 to M. And after I send it to just a set function without any restriction, but from GR to M. It's like the restriction of G linear just compulsorily force me to drop one component. It's like you add one more condition to make my freedomness reduce one position. Okay, isomorphism is given by this. It is easy to see it is an isomorphism. The point is you have to notice that any element of G n plus 1 can be uniquely written as this form. We want to stress that functions in CR twiddle have to satisfy one condition, while there is no conditions on functions in CR. The elements of CR are called inhomogeneous R cochain with values here. Inhomogeneous. We want to describe the co-boundary map using this inhomogeneous R cochain through the isomorphism R. So we define it this way, and by doing so we got a new complex actually with a new differential. using this, we're able to reconstruct our topic group, cohomology group. Here you see it's very obvious because there is 1-1 correspondence between G1 to GR, the 1 G1 G2. I mean there is 1-1 correspondence between these two, and here you are just defined as a set, but phi is as a G homomorphism. So once you can show that any element of Gm minus 1 can be written in this form, it means this is the general form of element in this way. Then okay, those elements actually form a basis of PR at the G module. So phi is determined by its image on those elements, and since phi acts freely on those elements, means this is a basis. You can define the image of phi on those elements anything you want. So this just tell you that this alpha phi is just as a set functions from those elements to M. The boundary group, the group of cocycle, the BR is the image of the R minus 1, and sorry, this is the boundary, the group of co-boundary BR, and the group of cocycle is ZR, the kernel of DR. This cocycle and co-boundary are terminologies from simplicial cohomology, as you can expect it, and this HR is just the group of cocycle quotient by the group of co-boundary in the simplicial cohomology. It just tell you how many holes are there. Remark that if M2N is a homomorphism, then this is given by composition. Yes, obvious. And if you compute explicitly, you have d0 divided d2 is in this way. Actually, we can define a function from G to M acting like this across the homomorphism. If there exists some M such that phi G is just Gm minus M, then we call this a continuous cross homomorphism. By defining those terminologies, we can actually realize each one and the group of cross homomorphism quotient by the group of principal cross homomorphism, and H2 similar description, very explicit, but when you actually want to compute what it is trying to do, usually we do not use definition to compute it. Usually we use long exact sequence deriving from some specific short exact sequence. Remark, if the action of G on M is trivial, then cross homomorphism corresponds to group homomorphism. Yes. Just from definitions of obvious. If the G acting on M trivially, this is just telling phi G is phi H and phi G, so phi just become a group homomorphism, and there are no non-trivial principal cross homomorphism. There are no non-trivial principal cross homomorphism, and if phi is just group homomorphism, then this is trivial. This is always true. No, this is true if and only if phi is trivial. Because in this case, Gm is just the M minus M is 0, so phi G acting on any G is 0, so phi is trivial. In this case, H1 is just homomorphism. Okay. So with this left exercise, we finish this section.